Hello everyone, and thank you for joining me in this video. I'm Kejia Zhang, a final year master student at AMT Lab, Xiamen University. Today I will be introducing our paper titled Towards Adversarial Robustness via Debiased High Confidence Logit Alignment, which has been accepted by ICCV 2025. Let's dive into the background of adversarial robustness. As you can see in the left figure, deep neural networks has shown incredible performance across a range of tasks. However, despite their success, they exhibit a significant vulnerability to even the subtle adversarial noise. Both discriminative classifiers and generative multi-large language models can produce incorrect results when exposed to such adversarial attacks. This highlights a major gap in their robustness. So, in the mathematical terms, adversarial attacks are often formulated as a maximization problem, where the goal is to maximize the attack loss, thereby introducing errors in the model's predictions. So, how can we defend against these attacks? One widely used approach is to treat adversary examples as a type of data augmentation. This leads to a strategy called adversary training. Formally, it's framed as a min-max optimization problem. We first maximize the adversary loss by finding the worst-case perturbation within a constrained space, and then minimize the classification loss over this perturbate inputs. Now we can know that adversarial attacks can push the models across the decision boundary, causing misclassification. Mathematically, this involves maximizing the attack loss, such as the cross-entropy loss. From here, a nature idea comes up. What if we minimize the loss instead? By doing so, the model should theoretically be more confident in its correct predictions. We define this the inverse attack. And of course, there were some small tricks involved when creating it. To understand where these high confidence predictions come from, we run two simple experiments. First, let's look at the visualizations. When the model faces adversarial attacks, excitation on the object foreground decreases. Now, under inverse attacks, the excitation does increase, but it shifts away to irrelevant background features. That's a problem. We can't allow the model to predict the class purely from the background. To go further, we also run a quantitative analysis. The results confirmed our suspicion. The model developed a spurious correlation. As the strength of the inverse attack increases, attention rises on both foreground and background. But here's the key. The slope of the increase is much steeper for the background. This shows that the model reveals disproportionality on background features. So, how do we fix this issue? We propose a very simple yet effective method. It works on two steps. Step 1. Removing focus from the background. We do this by computing the background logits and subtracting them from the normal logits. This simple subtraction performs a debiasing operation, and we then train the model with this debiased logits. Step 2. Restoring focus on the foreground. Now, suppressing background attention is not enough. We must also recover the model's attention on the object. So, we introduce a loss term. This loss ensures that in the feature space, background logits under inverse attack become unexplainable, forcing the model to restore its focus on the true foreground. It's a straightforward approach, but it works well. Our model's adversarial robustness improved significantly. At the same time, we can see that the robust gap dropped well, which indicates that we have a stronger generalization ability. The feature activation map conformness. We can see that our model maintains normal rotation, while the baseline models suffer from spurious correlation. And the quantitative analysis tells the same story. Our model consistently shows better alignment with the true object regions, validating the effectiveness of our method. That's all I want to share today. Thank you for your attention, and please feel free to scan the QR code to connect and collaborate.